Okay, class. Yeah? Prêt? Welcome to the second class on Matlab in engineering mechanics. Before we start, I have actually a question for you, and it has to do with the grades on the weekly homework assignments. I was hoping that your average grade would show up in the grade center. Did anybody see his grade? No? Do you have any information on how your homework has been graded? Yes. How do you know that?
In each exercise we can see the grade.
Yes. So in your individual exercise you see the 3 different gradings and the final grade. Oh, 2. Yeah, I'm sorry for that. Some people just commit to the system and then don't do their work. So you have to thank your colleagues for that. And in a sarcastic way. Yeah, I'm sorry, I cannot solve that. It's unfortunate. So the idea is if everybody puts in his penny, then you have 3 reviews. I was hoping that the average grade would show up in the grade center. It doesn't. I will contact again the feedback fruits, what's going on, and then that will be fixed. So don't worry. In the end, I always have a spreadsheet with all the stuff in there. All your individual comments on every issue is there. It's like a 1,000 by 1,000 thing, and that's saved. So don't worry. All the information is saved. Only it doesn't show up apparently in the grade center. That was my question for you. Is there any question from you to me at the moment about the course or the homework or other stuff? Yes.
What happens if our colleagues don't grade us?
Yeah.
Are we going to be penalized for that?
The question is, what happens when the colleagues are not grading you? So I will, if I translate it correct, if you get 3 reviews instead of 2 reviews instead of 3, what happens? Well, actually nothing. There's nothing I can do about it. You have to thank your colleague for that.
No, but what happens to our grade? It stays
Your grade is then the average of those 2, of course, and not 3. I mean, yeah. Which seems fair. Any other questions? Okay, then let's kick off for the topic of today. Linear equations, that's chapter 2 in the book. And then my question is, why linear equations? Where do you find these linear equations? That's the big question. Any ideas? Yeah, math work you find, but I mean more in your engineering work. Where do you find linear equations?
Everywhere.
Yeah, that is the answer. The only correct answer is everywhere. Moreover, if you have nonlinear equations, you usually cannot solve that, and you have to go to a system where you do linearize your equations. You get linear equations, you can solve them, and in an incremental way then you solve your nonlinear equations. So the final answer is you see them everywhere. And let me give you an example. A famous one is, of course, sum of the forces is mass times accelerations in the 3 directions. These are linear. Linear in the force, linear in the mass, and linear in the accelerations. Another one, sum of the torques, is a mass moment of inertia times angular acceleration plus angular speed cross product with I omega, the angular momentum. Now, I would also call this a linear equation, where maybe some of you would say, wrong. What is wrong? Why would this not be a linear equation? Yeah, the cross product. We see the cross product here is not linear in omega. So it all depends, of course, on what you want to solve. What is given and what do you want to solve? So yes, the equation is linear in the inertia, and yes, it's linear in the angular acceleration and linear in the applied torques, but not linear in the angular velocity. So you have to be clear about linear with respect to which variables, right? Then a famous one is of course this one, k times u is f, which pops up always at yeah, I have to repeat the answers because nobody hears it. But your voice is very little. Yeah. So the answer is finite element method. Yeah. So this is the classical finite element method equation where you say stiffness matrix times displacements is applied forces. A very powerful instrument, and also they are linear. In fact, they are not linear. It's a full nonlinear system, but we linearize it and we get these equations. Now, as an example. I like to look at this. And as an example, I like to do a finite element method of a two-dimensional truss structure. Yeah, that's how I call it. Structures. Yeah. Meaning those members are all pin joint. So you have members and they are all pin joint, and the only thing they can have is they can have tensile stress in them. No bending. That's too complex. So as an example, let me draw such a figure, like here. And usually you start with triangles, right? Triangles make up very stiff structures. Now this is basically a very simple structure. We have boundary conditions, B, C. Here, this one is fixed. This one has a support in only this direction. It can move here freely and in this direction. Then we have, of course, an applied force somewhere. What else? We need a coordinate system. That's always handy, right? Some origin and then some coordinate system. And then these guys, these are the elements in our system. And in our case, they're very simple. It's just a truss element. And these guys we call the nodes. And then the whole system is built up. You have a collection of elements, and then you connect them in the nodes, and then you have a structure. And it's like Connects or Legos or whatever, any construction system you have. Of course, in these members you have forces, tensile, so you have member forces. And the other thing is, of course, under the loading, and there's elasticity, so there are some displacements in the nodes. Displacements in the nodes. And that is the whole idea. So in this 1 hour, we are going to make a 2D finite element program for truss elements, for any system. Okay, how are we going to do that? Well, to look how such a structure behaves, we have to look at one part, and we have to look at what things do we have. Well, we also already saw we have nodes and elements. And what can we say about the nodes? So the nodes, if they are two-dimensional, then of course they have a position, they have coordinates. They are somewhere in space, so x, y. And under a loading, the system is of course elastic. Elastic elements. Under a loading, the thing will deform and we get displacement. So we also have in a node displacements. And for some magical reason, we call this displacements U and V. That's just how we do. We say, oh, in a node we have a U and V displacement. And actually, they are, of course, delta X and delta Y. But we're sort of sloppy or lazy, so we just translate delta X to U. Well, what do we have for the elements? Well, the elements are very simple. It's just one simple truss element, and the only thing it can have is a elongation, right? It can become shorter and longer, and that's it. There's no bending going on, meaning that we only have one deformation in the thing. So if the thing has a certain length, then of course the thing can change from length. So let's draw a general picture of this element. So we have an undeformed state, and starts in node P and goes to node Q, for instance, here. And so this is the undeformed state, undeformed. And then this node will displace, and this node will also displace, right? So let's draw something. What did I do? I said this is the displacement here, and here's the other displacement. Something like that, I mean, just random. So this is the delta x and the delta y at Q, and this is then the delta x and the delta y at P, or the U and the V. Then, of course, the element is now positioned like this. And if we had initially some length, some L0, then the length of this thing is probably a little bit longer now. It's L0 plus some delta L, right? Just made a little bit longer. It could also has become shorter, but that's just a sign convention. And the deformation we now define. That is a definition. The deformation is delta L. That's what we use for. Well, if this element has only one deformation and it has 4 coordinates, right? So we have x is the x in P and the y in P and the x in Q and the y in Q, and it has 4 displacements, delta x, but forget the delta x, we like to write u. It is u in P, v in P, u in Q, and v in Q. And of course we now, in terms of these deltas, we want to express what this elongation is in that element. Okay, so keeping that picture in mind, we want to write something like some linear expression, of course. So we want to write something like delta L is some matrix D times our displacements. And now the big thing is, what is this matrix D? So given the nodal displacements, what is the deformation? And I do a graphic approach here, so I just draw the bar in some arbitrary figure like this. So this was node P, this was node Q. Then initially, and this is with the L0, initially it makes some angle alpha with the horizontal. It's in some sort of direction. Then on top of that I write displacements, and I just take arbitrary ones. So here I have a U in P, a V in P, a U in Q, and here a V in Q. So initially this node will end up here, and this node will will end up here, right? But forget that for now. If I want to know what is the elongation, then I only have to look at the projection of these displacements on this bar. All displacements which are perpendicular to the bar, you can forget, because that is like a rotation of the bar. That doesn't make the bar longer or shorter. So I only have to take projections of the displacement, this part, and of this displacement, this part, onto the bar. And likewise here, I take this projection, and likewise here, I take this projection. And then I add up these projections, which is compression, and I add up these projections, which make them longer, and these make them shorter, and then the net of it is the elongation of the thing. Or in other words, the delta L equals, well, let's start, we can already write it in a matrix vector form, actually. So here we write these displacements, UP, VP, UQ, and VQ. Now, how does that work? Well, let's look at this UP. So I need a projection on this one. So that's cosine alpha. Yeah? And then cosine alpha, and it makes the thing shorter. Right? So it's minus cosine alpha. And then VP, that's this part, and then I need the sine. I need this horizontal part here. So that's the sine of alpha. So minus sine of alpha. Then here, it's the other way around. It makes the thing longer. So I need cosine alpha here, and I need sine alpha. Oops, okay. So this is this matrix D. Minus cosine, minus sine, plus cosine plus sine. So given a set of displacements, I multiply it with this matrix, and then I get the elongation. Let's take the super simple case of alpha 0. I see minus a 1, 0, 1, 0. Oh yeah, that's one part pulling, the other one is pushing. Okay, so now we have a nice expression for our deformation. Let's box it. Let's say delta L is d, and we know what d is now times u. That's one equation. So that's expressing our deformation in terms of the displacement. Now we have to connect these deformations to forces. Well, elasticity, linear, tells us, well, which law do we need? Hooke's law, right? Hooke's law, and what does Hooke's law say? Well, if you apply a force, then you get an elongation which is proportional to the force. Again, a linear relationship. Or in our nice technical terms, stress equals modulus of elasticity times deformation, right? Now, what is the stress? We use sigma for that symbol. Here we capital E and here epsilon. And these are all non-dimensional. Well, stress is newtons per square meter, and this guy has no dimension. Stress, it's a relative thing. So this also has the same dimension. However, we have dimensional things. We have a elongation, so we have to say, oh, that is easy. We have E, we have delta L divided by this L0. That's on the one hand side. And the stress, how do we relate that to our element? Well, our elements, and we need a small picture there, have of course some normal force, N. Some tensile normal force in them. And the stress in the member is then this normal force divided by the cross-sectional area. Or in other words, in terms of our variables, we now have that the normal force equals EA divided by L0 times delta L. Now we have our expression already for this guy. Now finally we need an expression for the member force in terms of the nodal forces. Well, that's also sort of easy. Again, you can draw a picture. You can say, oh, this is the picture. Here I have a normal force. And then the only thing I have to do, if this is the angle alpha, I have to find the horizontal and the vertical components of these guys. This was P and this was Q. Or in other words, our Fx in P, our Fy in P, our Fx in Q, and our Fy in Q equals, and then you just look at the picture and you fill in the numbers. Well, if this is N and we start at the beginning here, then the horizontal force is apparently minus, and it's the minus the cosine times this guy, right? So minus cosine alpha. And here vertical minus sine alpha. Horizontal cosine alpha. Vertical one sine alpha. Or in other words, and see the resemblance, right? Oh, make it a little bit smaller. Here I have a matrix and it looks almost, no, not almost, identical to the D matrix, right? And that's a famous thing which you can, by means of virtual work, you can derive that it is essentially the same matrix. Or in other words, we write down F, the nodal forces, are D transpose times the member force. And now we have a nice set of three equations. We have this one for the forces. We have an expression for this force in terms of elasticity, and we have an expression for this delta L in terms of our displacement. So we pop everything together, right? Put everything together, so we combine all the stuff. Here we go. So we say combine, and what do we get when we combine? We get F equals D transpose times, yeah, I don't want to write this long term, so I want to write something with an S. So this part I like to put here, and then I want to write an S here. S, and then say S equals. So S, and then D, and then U. And this is also a vector. So this is really our finite element matrix, right, for one member and also for the whole system. We usually write it then like F equals K times U, where in other words K is D transpose ST. Should be nice D. And that's basically it. That's our whole program. The only thing is, of course, that we have to take for every member, have to derive what this matrix is, and then we have to put that in the big matrix for the system, and then we have our system equations, add the boundary conditions, and then we can solve that. Yeah, I needed a little bit of water. Okay. So now let's look at the specific structure, and let's give everything a name. So the structure where I initially started with was these triangles, right? So it was this guy. And the first thing you have to do is, of course, you have to start numbering. You have to give everybody a name. So let's number the nodes. So we put a 1 here, a 2 here, and a 3, and a 4 and a 5. Now I also want to number the elements, and to distinguish these nodes with the elements, I usually encircle them. So these are element numbers. So this is an element number, and this is number 2, this is number 3, number 4, number 5, number 6, and this is number 7. What do we have? We have coordinates, of course, and how many? Well, it starts with x1 to y1, so I have to give my coordinate system, according to Heike. Oops, yeah, and the origin. And then that continues x2, y2, ta 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 ta, until, how many nodes do I have? How many nodes? 5, eh? Yes, so x5, y5. And the displacement, well, they are identical, of course, but just with another name, u1, v1, u2, v2, etc. until u5, v5. And of course, I have in all these nodes forces. So I have a force vector, and that's f x1, f y1, f x2, f y2, etc. until f x5, f y5. Now, I already derived for one element what the relation is between forces in the nodes and displacements. But now I have to do the whole system, so I need system equations. Go back to 100. So what are the system equations? That is the big question. So I know it on an element level. Well, for every node, I can write down that the sum of all the forces which come from the elements must be the applied force at that node. Right? Let me give you an example. Let's take, what did I take? Node 2. That's a nice one. Node 2, I have a number of elements coming in. There's element 1, there's element 4, there's element 5, and there's element 2. And all these elements, they have in this node forces. So for all these elements, I have to add up all these forces, and then I have the applied forces at the node. So that is how it works, right? Meaning that for every element, I have this expression, the element for that element, I have these matrices, and then I have to sum up these, and of course the displacement of all these elements in this node are identical. That means that if we form the big matrix of F and K and U, that let's write it like this. We have F1 here, F2, the force vector in 3. Oh, it should be a bit bigger. How do I do that? Throw this guy away. Yeah, and then just continue. So that's F4 and F5. So these are just the two-dimensional forces in the nodes. Then I get a big matrix. And then of course here on the right hand side I have the displacements in the nodes. So U and V in 1, U and V in 2, U and V in 3, U and V in 4, and V in 5. Now let's draw a grid that sort of helps a lot. So draw this grid, and now I have to draw this grid 1, 2, 3, 4, 5. Yeah. So nice 5 by 5 grid. And then looking at the picture, I have to fill in this grid in the sense element number 1 is an element which moves from node 1 to 2. So I have to, where do I have to fill this in the matrix? Well, it should be here. So element number 1 comes here. 1, 1, 1. Oh, go back. 1, 1. That matrix fits there because it's about these two forces and these two displacements. And the rest doesn't matter, right? Then the next one, element number 2, that runs from node 2 to node 3. So I have to add that in the 2, 3 part. So here I put element number 2. And of course I have to add it up, 2, 2, because the sum of all the forces are the applied forces. Element number 3, that's interesting, that's 1 to 4. So 1 to 4 starts, 1 is here, so that's number 3, and then 4 is here, 3. 4 is here, and 4 is here. And 4 is from 2 to 4. Well, you get the picture. You just fill in those matrices, you add them all up, and then finally you have your system matrix. And then given that system matrix, which is our F equals K times U, then these are usually given, and then we want to solve these. And there we see we have our linear system of equations. Of course, we have to put in boundary conditions that some things are fixed, but that's a detail for now. We will fix that in our program. It's not so interesting. Okay, any questions on this? Is that clear? Let's do some Matlab. Now I need this sketch of the figure in the top left, because I need this numbering. Yeah. Then we go to Matlab, lecture 2. Yeah, okay. Oh. It's okay. We can start here. Yeah, let's start with some new file. Oops, Java. I don't know. Program truss, and what do? What's in this next line? Sorry? By whom? Exactly, by whom? By, and I usually also put in the date. Yeah, okay. Well, how many nodes do we have? Number of nodes? 5, right? Oh, there's not nodes. Number of nodes. Yeah. Number of elements is. Yeah. Let's put this a little bit smaller, and then we can see. Yeah, we can see the figure, right? What was the number of elements? 7, eh? Yeah. Okay, now, yeah, we have a number of data to process, so we have to know what the coordinates are, right? So at the nodes. So maybe we make an array with xy, so xy, and that is, and then the first coordinates is the x, and the second is the y, so the first 0, 0, that's clear, right? That's the origin. And then the second one, well, that's the midst of the structure. Well, I haven't talked about that, but let's say that the dimension is W, right? So the width is just W. So then again we have to define here a W. So we say width, so W is 10 meters or something like that. I work in SI units. Why do I do that? Well, then I can easily change the dimension of the structure with only one parameter instead of typing all the way here. So what was this? W over 2, 0. And node 3 is, well, W0. Oh, that's easy. Node 4. Yeah. How does that go? These angles are 60 degrees and 30 degrees. And I remember something with 1/2 and 1/2 square root 3. Do you also remember that? If I have this triangle, this is 30 degrees. If this is 1, then this is 1/2, and this is 1/2 square root 3, right? Something like that, and then we have to put that in. So apparently, yeah, then that's W over 4, and then the height is this W over 4 times square root 3, right? And then node 5, well, that's 3 times W over 4 and W over 4 times square root 3. Okay, so those are the nodes. What else do we need? Well, we need to describe how the elements run, right? So elements, yeah, the elements, they run from one node to the other. So element 1, the first one, runs from 1 to 2. And the second one runs from 2 to 3. And the third one runs from 1 to 4. Where are we? 2 to 4, right? 2 to 5. 2 to 2, where am I? 3 to 5. 4 to 5. Yeah, that should be it. However, the elements not only have nodes by which they run, but they also have a cross-sectional area, and they have some elasticity modulus. So I also have to create an array of elasticity modulus for those 7 elements. And I also have to create an array for areas. And then when I calculate the stuff, I have also get an array of normal forces. But all these things belong to the elements. And I like to keep everything together. Is there a way to keep data together in Matlab? Sorry? A cell array is a way, and the other way is? No ideas? A structure, yeah. So there's a structure, and let's demonstrate that on a very simple example. Suppose you want to make a database of your friends, and so your friend, you have a friend, and the friend has a name, right? Then you just put a dot and you say friend.name, and then you can put in his name. So friend.name is Ari, for instance. And you want to remember his birthday, so you say friend dot well let's do age. That's otherwise I have to type too much. Friend, where are we? Friend dot age is 64. So what do we see now? And that friend is a struct, and it has 2 fields. It has a name, which is a string, and it has an age, which is a double, a number, and so now I can pass on this thing, and not only do I have this one field, but I can make an array of these structs. And now we're in business, because if we make an array of this, then we have one entity which holds all this stuff. So let's redo our whole thing. Let's go back to our initial problem. This was a good idea. The widths we need. Widths we need. But this has to go. We have to do this in another way. So we are going to make structs. And we're going to put all the information that's necessary in that one struct. And let's start with the elements. So we say element. Oh no, that's not element. Element, yeah. And you could say element array. That's maybe a nice way for programming that you understand. Oh yeah, that is the whole container with all the elements. There is this there is this thing on the website about the art of programming in Matlab, an example and I think this is a way to do it. But please read it. Anyway, we write element array, and then we could say, well, the first one. And dot, and now we have to come up with some fields. Well, for the elements we have to know the nodes, right? So the nodes in this case are from node 1 to node 2. And let me finish element array 1. The other field we want to know is the elasticity, the modulus of elasticity is, what is it, 210 E9 or something like that. And the next thing we want to know, we want to have a cross-sectional area for the thing. So element array dot a for the cross-section one. Sorry, this is number 1. It's still not element. Yeah, I'm dyslexic. Yeah. Like this, right? Equals, and then we have to pick a number 1e minus 3 or something like that. And then we can continue typing like that. What you could also do, so that is the basic idea we want to do, but it's maybe also nice to first allocate space for all the 7 elements. So then you make a loop, you say for j is 1 to number of elements, and then I'm gonna make this whole thing. Element array. I give it the index, j. And then I say it is a struct, because you can say I make this thing struct. And it has a field called node. And for now I put in zeros, because I will fill the right numbers later on. It has a field called e, and then I put the default value e9. And it has a field, a cross-sectional area, and then I put in this value. And if I do this, then I create, let's get rid of this for now. Then I create 7 of these elements, and the nodes are not filled in yet, but standard there is this material stuff filled in. So let's run it. Test 1 we say. And then see what we get. So whose, let's clear everything. Let's get rid of all the junk. Yeah. Let's run it. There was no problem. Let's see what we have. Whose. So apparently we have a 1 by 7, a struct, and then now I want to inspect the data, and that is a bit tricky. So you can write element array, and then you can hope that you get stuff. But this is all it replies. It says, well, element array is a 1 by 7 struct array, and these are the fields, and that's it. And why does it do it like that? Because if it would print it, it would probably fill the whole screen if it's a bit size of an array. There's another way maybe to do it, and to identify a single field, for instance this A, and then I get 7 times an answer. I get 7 times the cross-sectional area, because there are 7 elements. So working with structs, arrays of structs, is a bit different than working with arrays. It's a bit trickier with what you get. But essentially you can do all operations. Okay, so let's proceed. How do we proceed? So we filled everything, we put all zeros there. We could check that, by the way, by saying node here, node. Then we get 7 times 0, 0, 0, 0, for all the 7 elements. Okay. What we want to do now is fill it with sensible things. So the only thing we have to change now are the nodes. So we write element array, and then the first one, and then for that I want to change the field node, and that is 1 to 2, right? And then we have to do with, I usually do with copy and paste, although it creates errors. Let's see, we have to do 7 times, something like this. Is this 7? Yeah. And then we do 2, 3, 4, 5, 6. That's not 6, 6, and that is 7. And we put in our numbers. So again, then we look at our figure here, right? 1 to 2, 2 to 2 to 3. This one is 1 to 4. Number 4 is 2 to 4. Number 5 is 2 to 5. Number 6 is 3 to 5, or 5 to 3, as you like it. Doesn't matter much. And 7 is 4 to 5. Okay, let's run it again. So no errors. Now again inspect the field node of all the elements, and what do we see? Before you hit return, you should always have an idea of what to expect, right? Same with meeting a new friend. You don't open your visor before you know what's going to happen. You must have an estimate. A good knight performs that way. Okay, what do we expect? Yeah, speak up. Sorry?
The connections of the elements.
Yeah, so I would expect 7 times a line where I see 1, 2, 2, 3, 3, 4, that whole list. Yeah, that's exactly what we put in. So, okay, so we can inspect the structure. You can also inspect it here, of course, in that inspector thing, but I hate this thing. I cannot work with that. I always like to work with the prompt there. Anyway, so we now made this stuff, the connectivity of the thing, but we not only have elements, we also have nodes, right? So for nodes we can do the same thing. So we say for j equals 1 until number of nodes. Any idea why I use j and not I? Has anybody an idea? No? Usually you use I. Well, I by definition is the imaginary unit in Matlab. So if you type I, then you get this. Because by standard, numbers are imaginary, have a real part and an imaginary part, and the imaginary part is defined as I. You can overrule it, you can say I is 3, yeah, and then your whole imaginary thing is gone. And then you have to redefine it again and so on. So therefore I usually don't use I as a count, J or K. But you can do it, it's no problem. Okay, we're going to make a node array, right, in the same format, J. And now we have to decide what is in a node. Well, the first is obvious, right, coordinates. And let's put them at 0, 0. Then of course a node also has displacements, U and V as we said. So UV, that's the thing we want to calculate, but for now we just put in zeros. It also has applied force, right, in a node. So a nodal force, Fn, also a vector, 0, 0. And of course nodes have boundary conditions. Either they are fixed or free. I call these BC here from boundary condition. And then what did I do? 0 is free, apparently. That's my format. So I made a struct with 4 fields. I have the coordinates, I have the displacement, I have the applied forces, and I have the boundary conditions on every node. We can run it and see if we get errors. We get no errors, so that sort of works. Then we have to fill in with numbers. Well, the thing we have to add, of course, is coordinates. So we have to say node array 1, sorry, for node 1, we have to put in the xy coordinates, which are, well, in this case 0, 0, so it was not necessary, but let's do copy and paste. We have 5 nodes, so that's easy. So this is 2, that's 3, that's 4, and that's 5. Then here we put in the numbers we previously did, like w over 2 and 0. And here the end was w, 0. Then here we have, what was 4? Oh yeah, that was a w over 4 and w over 4 times square root 3. And then this was 3 times w over 4 and w over 4 times square root 3. Okay. Now we also have some applied force, and that's only forces. That was only at node 4, right? It's not in the picture, but if I remember well, we had a force going down here. So, meaning, and that's the beauty, initially there are no forces, so, and we only have to write down then a force for that node. So, this is then Fn, from the applied force, no x, and in the, minus 1 E5 or something like that, some number, 100 kilonewtons or in the downward direction. Boundary conditions, yes. Because we have, of course, fixed nodes. Sorry. Yeah, 4. Thank you. Very good. Very attentive. I like that. Then node 1 has a boundary condition, and the boundary condition there is that both in the x and the y it's fixed, so I say 1, 1. That's just my rule for when it's fixed it's 1 and when it's free it's 0. And then we have another boundary condition on the last node, if I remember well. Oh no, node 3. And that is in the y direction. This defines everything. This is our data structure, and it took some time to build it, and that's important because we have to work with that. But the beauty is now, if you want to make a calculation routine, the only thing you have to pass on is a variable called element array and another variable called node array, and that's everything, because everything is in there. What is the first function we're going to make? Stiffness matrix, or maybe something else? How do we know these numbers are correct with the connectivity and the coordinates? By drawing it. Just draw it. Just tell somebody, well, node 1 is this with these coordinates, node there is there, and just draw the whole thing. And then draw the elements. Right? Are we going to do it ourselves, or are we going to automate it? Sorry? Yeah, please speak up.
Outsource it.
Outsource it, to a function. Let's write a function. If we write a function, draw the structure, then we can put in any structure and we can check, is it correct? So let's make a function. Draw structure. And the input is, the element array, of course, element array, but it can be any element array, and a node array. Now, of course, in our mind is the idea like, how is this structured, this thing? And then for the help, you have to do this with a percentage, something like this, right? And then the author name, and the date. Okay. Now we're going to draw it. So if we want to draw the elements or the nodes, let's do the elements, right? So let's start by draw all the elements. Oh, that's almost right. Then we have to loop over the elements. How many elements do we have? And elements is, it depends. It depends on what argument you put in. Yeah? You don't know. I mean, somebody else can come with a structure with 516 elements, and then you only draw the first 7. That's not what you want.
Size of the structure.
Yeah, yeah. So you say 1 until the length of element array. End. Oh no, not end yet. 4. I was a bit too quick. So for, you could say for j, that's the element, is 1. Oh, this was too quick. And is that until the n elements end. So what are we going to do? What do we need to draw an element? We need the starting point and the end point, right? So we need the p node, and the p node is a element array j. It's not element array j. That's, we're operating now on number j, and then node 1. That's the p node. And the q node, yeah, that's the second one, right? So you do this. Q node is number 2. So now we know it runs from 1 to 2 or 3 to 5, and now we can pick up the coordinates of those nodes. So we say the point P, where is that? Well, then we need the node array, and then we put on the P node. Well, and then we need dot xy. We need the coordinates of that guy. And likewise for Q, the point Q, we can say we take the node array, we take the Q node, and there we want the xy values. So now we have xy coordinates, that's P, xy coordinates of Q, and then the only thing we have to draw is a line. And yeah, so we say plot. So we need, if we need first to put all the x coordinates, so that's P1 and Q1. And then we need the y coordinates, that's P2 and that's Q2. And if we draw a new line, we want to keep this one. So hold on, I want to draw all the lines together. I guess this should work, sort of. Does it look like Matlab? Okay, save. Yeah. Yeah, let's give it a little bit different name. Error handling, oh yay. Okay, well, let's run the thing. Well, we cannot run it here, we have to call it, of course, so we have to say this function in our test one. So we say draw structure. Now this, like this. Looks a little bit like it. Not completely, right? What's wrong?
The scales of x and y should be the same.
Yeah. So Matlab usually tries to fit everything nice in the window, and we want an equal axis. So maybe we should say that somewhere. We could do it in draw structure. We could do it also outside draw structure. Well, for now, let's say here x is equal. Let's see what happens. Yeah, that looks better. Then we see all kind of strange colors, which you can change, of course, if you want to. How do you change that? And I see a very thin line. I want to have more thick lines. So, for instance, if you keep the handle of this plotted line, just as a variable, then with that handle you can do all kind of cool things. So in this case I'm going to set the line width a little bit more. Line width What did I do here? 2. Okay. And then we save it, we run our program, and then we see nice thick lines. And if you want to set the color to some value, well, we can do that too. I want all the lines to be red or whatever. Here we go. So now I actually want to know who is who. Because suppose you made a mistake and then you don't know where did you make the mistake. So I want those element numbers here. Ideally even in a circle, but let's forget that for now. How do we put element numbers here? No idea? Really not? Oh, okay. Well, we have the 2 points, so we can calculate what the midpoint is, right? So midpoint is point P plus Q divided by 2. That's the beauty of Matlab. 2 coordinates, add them up, divide them by 2, and you're in the middle. And then we want to put a text. Okay, so we set the text at the midpoint. And what is the text? Yeah, the node number. And that is, yeah. You are tempted to write J here. But that doesn't work because J is not a string. J is an integer. So you need to have the string representation of a number. Now, how do we find the string presentation of a number? So if you have like, well, J is 5, for instance, and I want to have the string, which says 5. Num to text. Num to string, maybe. Num to string. Yeah. That's a very basic one. There's also a very elegant one, and that's called sprintf. And that's a very, there you can do all kind of cool things with formatting and so on. In the example, which I will put on the web after the lecture, I have used sprintf. But for now, I will do simple num to string and then j. Now if we run this, then hopefully we will see an error. Yeah, what did I do? Text. Oh yeah. Oh, it needs the x coordinate and it needs the y coordinate. Okay. I thought I could use a vector. Where's my figure? Figure, where are thou? Here. Yeah. Ah, 1, 2, 3, 4, 5, 6, 7. Well, you can imagine you can go on and on like this. If I can draw the structure, then I can also make for every element a K matrix, and I can also add for all these K matrices in a big matrix. I mean, the trick I showed you now by making a function, putting as input these 2 structures, elements and nodes, and then doing some operation, you can do now almost anything. Now, with respect to time, I'm not going to type that here, but I'm going to show you, and I'm going to put the stuff on the web after the lecture. Lecture 2, this is program truss. Yeah, and this is now my program. And the program is actually relatively short. It initializes the data, it makes a stiffness matrix, it uses boundary conditions. This is the only line where it solves the linear equations. Then it adds up the displacements to the coordinates, and then it draws the structure again with the displacements. So let's look at one of these functions. Let's look at, for instance, stiffness matrix, just to show you that it's basically the same type of thing like draw structure. Input is element node array, output is a matrix. I find out how many nodes there are. I allocate space for the K-matrix. That's always a good practice, to first allocate space and then put in the numbers. And then I run again over the elements. I pick the two nodes. I calculate what the length is, the initial length, the angle of the thing. I make the D matrix here. The S matrix, I make by taking out the A and elasticity and area, cross-sectional area. Then here you see this element matrix, and then there's a trick to put them in the big matrix. And that's all. And then I have made the stiffness matrix for the system. Now how does it initialize the data? How does our initialized data look like? Well, it's almost the same as I typed during the lecture here. I think it's almost identical even, besides some naming here, loop variables. Okay, let's run the program. So what does it do? It makes the stiffness matrix, calculates displacement, shows the deformed structure with some scale factor, otherwise you see nothing. And I think the scale factor is 100. And then plots that on top of that. In green we see the undeformed structure. This is the force. And in, and in red we see the deformed structure. I will put the program on the web. Look at it because it's part of the assignments. The last assignment is on this program. You have to extend it a little bit. And I'll see you all next week when we talk about zeros and roots, I think. But I don't know for sure.